Okay, so let's go ahead and take a look here at our PowerPoint. Review PowerPoint, couple of fun things to take a look at. Sorry, my tablet was just, I guess, getting instituted here. So the Review 1 PowerPoint. I start off here with providing nomenclature words that are frequently used in the free response questions. Calculate, describe, determine, estimate, explain is a big one. And there's explain hows, there's explain why. Definitely take a look at the different options there. Identify, indicate, circle. Justify is another big one that they use in AP Chem. Make a claim, definitely make a claim. And then you have to provide evidence and reasoning. So we call that claim, evidence, reasoning. I'm going to show you a few examples of this also in the PowerPoint today, although we've been already using that claim, evidence, reasoning strategy for answering some of these questions. Predict, make a prediction, represent, draw, or write. Those are more for those particular model diagrams and graph questions. I don't know if there's much in Unit 1 for you to do there for the drawing, but you'll see some in the future as well. So basically, it goes by topic in the PowerPoint. 1.1 here, moles and molar mass, kind of outlining what you're supposed to know here. Remember the mole map, you're supposed to be able to convert there. You need to also be able to use this equation where you can find moles or molar mass. Those are the important parts and facts of this particular topic strand. It goes through all the topic strands that I've gone over so far, all the way through 1.8 and 4.5 and 3.7, what you need to know there for those particular strands. But we're going to start off with the very long free response that kind of does a lot of interconnecting and also reviews hydrates. This one I noted here, even though there's probably also some 1.4 stuff in this particular free response as well. This one incorporates lab procedures and lab analysis in addition. So there's lab stuff in here that you're going to need to be able to answer. Use the following questions relating to gravimetric analysis. Well, we did a gravimetric analysis lab, so we're going to have to recall some of the procedures and things from that. So studying your gravimetric analysis lab is also going to be important, and I plan on grading those and getting those back to you this weekend as well. So this is a prior free response question from a previous exam, and we're going to go through it line by line, giving you an idea of how to calculate and proceed here. So this beginning part of the problem has parts A through part C, and part B actually has 2 parts to it. Lots of different things to kind of unpack here. In the first 2 experiments, a student was assigned the task of determining the number of moles of water in 1 mole of magnesium chloride, some hydrate over here, N hydrate, okay? Now, if you don't remember what hydrates are, let's quickly talk about that. You have an ionic compound. Now, some of the water incorporates into the ionic compound structure, so that's why we have N waters here, certain amount of water molecules in there. The 2 combined, this is what's equivalent to the hydrate. Now, separated, MgCl2, the correct terminology for the ionic compound, this portion of it would be the anhydrate. The other component would be H2O, okay, so adding in those water molecules. When you add these 2 things together, you get the hydrate. But if you just have the MgCl2, only the ionic solid without any water in it, this is the anhydrate. Now remember in our gravimetric analysis lab that I did where we had our unknown M2CO3, we said that this one was hygroscopic, where it does absorb water from the atmosphere. And that's why I had to heat it in the crucible 3 times to drive off all the water so that it would be anhydrous. Same idea here, the anhydrate, anhydrous. That was the purpose of doing that procedure, was to make sure all the water was driven off. Now, first thing here, they give you a data table with lots of information, so you're going to need to glance at that. We have the container, initial mass of the sample in the container, mass of the sample after the first heating, second heating, third heating idea. Now we did this also in our gravimetric analysis lab, where we did the repeated heatings. Does anybody remember, explain why the student can conclude that a hydrate was heated a sufficient number of times in the experiment? What was the purpose of the heating, and when did we know we could stop? Why did they know that it was sufficient? Yes, because the mass doesn't change. For the last 2 heatings here, the mass pretty much stabilizes. And when the mass stabilizes, you know you've driven off all of the water. So that would be the first part there. So I'm kind of going step by step through it, explain why the student can correctly conclude that the hydrate was heated a sufficient number of times. The mass of the sample was virtually the same after both the second and the third heatings, showing all the water had been driven off. That is a sufficient explanation for part A. On to part B. Use the data above to calculate the total number of moles of water lost when the sample is heated. And then part 2, which we'll get to in a minute, is determine the formula of the hydrated compound. Now, 2 components. We have our anhydrate here and the water part. Remember, those 2 things added together give us our hydrate. Those 2 things together. Now, to find the water though, which 2 things appear on our data table do we need in order to figure this out? What 2 things do we need? What pieces of information? Initial, good, and the final heating, the third heating, right? Now, we don't really need to concern ourselves with the container too much, because the container is in both of these values. So when we subtract those values, we're really also getting rid of the container as well. Does everybody see what I'm talking about? So we would set this up where we would take our initial, which this is the hydrate at this point because it's initially here. After the third heating, the only thing that should be left in there is the anhydrate, because all of the water should be driven off at this point. Subtract out the anhydrate, and we get 1.848 grams. Now, so this is the hydrate minus the anhydrate. That's going to give us our water mass, okay? That's part of it, but we don't need the mass of the water. We need the moles of the water. So what do we need to do here?
Convert it to moles.
Yes, we want to convert this to moles. And what do we need to convert in order to get to moles? Molar mass. Molar mass of water, 1802. Use your periodic table if you don't have that one memorized. That equals 1 mole of water. And 1 mole of water, then we calculate with our calculator here. And we get 0.1026 moles of water. So far, so good. Got that part down, not too hard. The hard part is like, what do I need to pick up out here of my data table? What do I need here? So far, so good. Set that up. And as you can see in my PowerPoint for the review, I pretty much write out all the steps for you so you can review. Also, I am recording this and you can review it on YouTube if you need to. Now we have to determine the formula of the hydrated compound. This is a little bit more complex, finding the formula. Okay, we know the moles. I'm going to write the moles of the water down here because I'm going to need that later. Moles of my water was 0.1026. Okay, I'm going to need that later. But before I can do that, I need to have some information about my magnesium chloride. And the relationship between the formula, we need to find this N number. We need to know what this coefficient is here. And the way to do that, if you don't remember the hydrate lab from last year, to find this N number, it's going to be moles of the water divided by the moles of the anhydrate. Anhydrate. That gives you your N number. So if you don't remember that, now you do. So now you're refreshed with your hydrate math. How do I get the moles of the anhydrate though? They only gave me masses up here. I need to find the mass of the anhydrate first. So that's the first thing I need, mass of the anhydrate. Which two values up there do I need to subtract in order to get that mass of the anhydrate? Good. So we need our container and our final heating. The final heating is the anhydrate, but we need to subtract out the container now because that's, you know, also factored into this mass of the third heating. So let's go ahead and do that. Very good. I knew there was a reason why they put that container mass up there. I was eventually going to have to use it. Although sometimes they do provide you extra information that you really don't need. And it's just there to as a distractor. So be aware of that as all. That sometimes it's a distractor, sometimes you're eventually going to use it. So calculating this is my anhydrate, which happens to be the magnesium chloride. Now that I have the grams of the magnesium chloride, I can easily do what? What am I looking for again? Oh, I need the moles of the anhydrate. There we go. Not the moles of the water. I already have the moles of the water. I need the moles of the anhydrate. So I'm going to change that to moles. MgCl2. Now the molar mass of magnesium chloride, magnesium is 24.30 on the periodic table, and the chlorine is 35.45 times 2. So the calculation there ends up giving you 95.2 grams MgCl2, and then 1 mole MgCl2. We calculate this, do the math, divide it out, and we end up getting moles of MgCl2. Now that we have the moles, and we also have our moles of water up here, we can figure out our N value. And once we know our N value, we can write out the formula. So that's important. So let's go ahead and do that division, where we take our 0.1026 moles of the water, we divide it by the moles of the anhydrate, and what do we get for our N value? I believe it looks like it ends up being 5.99, which of course rounds to a 6, correct? So then when you're writing your formula, it would be MgCl2, put the dot there, 6 waters. 6 waters. So this would be our formula for finding part 2. This is B part 2, and you need to make sure you label, you know, what part you're answering with your work. So you can see this one took a lot of work to get to the answer and proving the answer. I also, like I said, typed it out here, set it up for you so you can refer to it in the PowerPoint. Finding the mass of the anhydrate and how to find the N in the formula, reviewing how to do that. getting your overall formula there. Now let's look at C. A different student heats the hydrate in an uncovered crucible and some of the solid spatters out of the crucible. This spattering will have what effect on the calculated mass of the water lost? Justify your answer. Here's that justify popping up. So the spattering part, we need to decide what is that going to do to our data here? Which part of our chart is that going to affect? Which value on the chart? If some of it spatters out. Let's think about this. We're heating it up in the crucible, right? Okay. Well, the initial mass, this one, this is what we found out, you know, beforehand, before we started heating. This is before heating. So that one shouldn't be affected, right? Because that's the initial mass of the hydrate. That has both components in it. We start heating it, though, to drive off the water. So we have our crucible here with our stuff and it spatters out. Which ultimate value is going to be affected? The anhydrate. So this value right here should be what? If some of it spatters out, is it going to be 23.977 anymore? No. What's going to happen to this value? Is it going to be greater than or less than it should be? It's going to be less than it should be. Exactly right. Less. So let's think about this. How do we find our water mass? Okay. Hydrate minus anhydrate gives us our water mass, right? But this value is lower or less than it should be. So what happens to the water mass overall? So this value is less than 23.977. When we subtract it now, we're going to get a greater difference for our water. Yeah, this water mass will be greater. It'll be greater than it should be. So the effect on the calculated water mass, it's going to end up being greater than it should be. Now let's look, so that would be the claim part. The water will be greater than it should be. What is the evidence part that you need to cite? The spattering, you know, means you've lost mass of your anhydrate. That's the evidence. Spattering out means you're losing something that was in the crucible. The reasoning, when you do the subtraction to find the water mass, your anhydrate amount is lower. So therefore, your water mass will increase. So let's talk about that claim, evidence, reasoning statements here. The claim, the mass of the water loss will be higher than it should be. State your claim. Evidence. Spattering removes the anhydrate hydrate from the crucible, and that completely alters and lowers, reducing the mass of the anhydrate. This calculated value in the chart. Now the reasoning, when you go to analyze your data, the difference between the hydrate and the anhydrate now is going to be greater, and thus calculating the higher water mass. So claim, evidence, reasoning, that's how you should approach these as you're explaining. But some people start explaining before they state their claim, and I want to warn you not to do that. Make sure you make your declaration first. I think it's greater than, I think it's lower than, you know. Make sure you make the claim first before you go explaining, because then you lose that point for not making the claim. Even though your explanation could be beautiful and wonderful, you forgot to make the claim. So always make the claim first. All right, so the second part of this example, now this problem continues on, but it's altered now and it goes into a new form. So they're taking the magnesium chloride and they're doing a second experiment. So here it's building on, and it's going to go into different concepts, and it's going to connect in different concepts. Student was given 2.94 grams of a mixture. So that's why I said the mixture part's coming in, the 1.4 here, containing anhydrous magnesium chloride and potassium nitrate. To determine the percentage of the magnesium chloride in the mixture, student uses excess silver nitrate to precipitate the chloride ion as silver chloride. Remember, silver chloride, it's telling you is going to form a precipitate. And when we have precipitates, guess what we can do with precipitates in the lab to get mathematical calculations? What can we do? Or what did we do? I guess I should phrase that better. What did we do in our lab? How did we find that mass? What was the procedure of the lab in order to get it? Yes, we want the mass of this silver chloride. But procedurally, what did we have to do to attain that mass? We filtered it, exactly. This is where we did gravimetric analysis. Anytime you have a precipitate and you want the mass of that precipitate, you are doing gravimetric analysis and you're going to filter it. So that's what this question's all about right here. Starting with this gram sample mixture dissolved in water, briefly describe the steps necessary to quantitatively determine, that's finding that mass, of the, silver chloride here. Silver chloride precipitate. So that's the first thing. What were the steps of the filtering? What did we do in order to find the mass? Okay. So let's go ahead and recall those procedures. This is the lab procedure question. Solutions producing a precipitate can be filtered out using gravimetric analysis. So let's go over the steps of what you would need to write in order to get the point. First, you would say I'd filter the precipitate from the reaction. This is the detail that they want, so you don't have to go beyond this. Then you're going to wash the precipitate with DI water a few times. Does anybody remember why we do that? Why do we wash it a few times before we let it dry completely? What is the purpose of the washing? To make sure none of the other ions stay behind. Some of them could, attach to the precipitate or the filter paper. So you want to keep washing them through to make sure they're not adding to the mass. Exactly right. Once you've finished washing it, you need to let it dry completely. Why do we need to let it dry completely? What would happen if you don't let it dry completely? What would also be in there adding to the mass? Water, yes. So we have to let it dry completely because we don't want water in there adding to the mass. You're right. Once you have the mass, then you can subtract out the filter paper to get the mass of the silver chloride. So this is the brief descriptions. You're not going into huge detail, but you're hitting the main points of the procedure for gravimetric analysis and filtration. And that's what you would want to do there. Now let's talk about E. Okay, determining the mass of the silver chloride precipitate, they gave us the value. This was what was measured on the scale, on the balance. This is what they measured on the balance, okay? Based on this information, calculate the following. The number of moles of magnesium chloride in the original mixture, and then the mass of the magnesium chloride percent in the original mixture. So if they gave me silver chloride and I need to find moles of magnesium chloride, what do I need to do here? What kind of math problem does this become? Well, I have one substance produced. This is a product of the reaction, right? And this was in the original mixture to begin with. So this must have been a reactant. Yes, this is stoichiometry. Exactly right. So this is stoichiometry. And what do you always need in stoichiometry before you can do anything? You need a balanced equation. Exactly right. So we have to, in this particular problem, they're wanting you to figure out the balanced equation. Now, I will warn you on Wednesday, I'm not going to have you do that. If there's a stoichiometry calculation that needs to be done, I will provide you with the balanced equation. because we haven't really gone over balancing yet. But we can just practice real quick and try to recall some of the balancing and predicting of products from Chem 1. Now we know one of our reactants is magnesium chloride. What does it say I'm reacting the magnesium chloride with? What's the other reactant here? No, that's in the mixture, right? The KNO3 is in the mixture. But what am I actually reacting it with to get the silver chloride to precipitate? Yes, silver nitrate. I'm reacting it with the silver nitrate. Very good. Now, we know one of the products is silver chloride. We need to figure out what the other product is. What other two components? Well, we have magnesium and we have nitrate here. How can I figure out the formula for magnesium nitrate based on the information provided? These are all ionic compounds, so what do I really need to know about them? Their charges. So magnesium, what group is magnesium in? What charge would that be? It would be 2+, good. Now, even if I don't know and don't have nitrate memorized, can't I figure out the charge based off of the KNO3 and the silver nitrate here? Can't I figure out the charge if I don't have it memorized? If we have potassium nitrate here, what's potassium's charge? It's a +1. It's 1 to 1 here, so that means nitrate has to be a -1. Good. So now if I know that nitrate is -1, can I not figure out the formula? All I have to do is cross now, right? Yeah, so we get MgNO3 2. So that is my last component here in my equation. Now I can balance the equation because I have it set up and I have everything written out correctly. So, looking at my equation, which components are out of balance? Which ones do I need to fix? Yes, AgNO3. There's 2 over here on this side and only 1 over here. So what do I put in front of this one? Gonna put a 2 there, good. Now, what else is still out of balance? Ag, yes, Cl. So I have 2 silvers, 2 chlorines. What should I put here? 2. Good. Now that I have my balanced equation, I can do stoichiometry. Once again, I'm not requiring you to balance stuff on Wednesday. I will provide you those balanced reactions. Later on when we get to, I believe it's Unit 4 is when we'll really get into balancing. Okay. So now we have our balanced equation. Now we can start looking at our stoichiometry. So if I have grams of silver chloride to begin with, I need to change my grams of silver chloride to moles. Find the molar mass on the periodic table. Silver is 107.87 and chlorine is 35.45. So this ends up being 143.32. At this point, what step comes next in the track? The mole ratio, good. So I'm going to take the moles of the silver chloride and put them down here. And I need to go to moles of my magnesium chloride. Go over here to the balance equation. 2 moles of silver chloride equal 1 mole of magnesium chloride. Now that I have that, I can do my calculation. Divide by the 143.32 and then divide by 2. And, is that right? Yes, it's right. 1 moles. MgCl2. Now I have my moles. I've got that part down. That's correct. I need to do percent by mass of my magnesium chloride. So this would be the answer to part 1 of E. For part 2 of E, what do I need to do with this value that I calculated here? Because I need to do a percent by mass. Convert it to mass, exactly right. Okay, if you remember from previous part of the question, we already found the molar mass of magnesium chloride, which is 95.2. Oops, that doesn't go there. I didn't do my diagonal down right. Let's do the diagonal down right. What goes on the bottom? Moles go on the bottom. So the grams must go on the top. So the 95.20 goes on the top, the 1 mole goes on the bottom. Now I calculate my mass of the magnesium chloride that's in that sample, that mixture, 1.82 grams. So now I know the grams in the mixture that actually was from the magnesium chloride. Now percent by mass, remember, is like part over whole times 100, because we're talking about a percent here. So in this case, the part is going to be the grams of the magnesium chloride. What is going to be the whole that we need to divide by? Yes, the entire mixture, the grams of the mixture, and they told us it was 2.94. So we need the grams of the mixture here times 100. And then you go ahead and do that calculation, 1.82 divided by 2.94 times 100, and you'll end up getting your percent. Times 100, it's going to looks like it's going to be 61.9%. That would be the final answer. So we did part E1 and E2 here. You should notice in this particular example problem, we started out with some 1.1 soft molar mass. We did some lab procedure in here, and we added in the stoichiometry and percents. So lots of different concepts all meshed together in one free response question. And you should expect the free response questions to do that, where it may start out with a math problem, then they're asking you a conceptual problem about the compound, or a lab procedure, things like that. They do not just necessarily always ask exactly, from the same concept. So you need to be prepared for that. That was the purpose of showing you this example. So that's part, this is E1, excuse me, not D1, but that gave us the moles of the magnesium chloride. And here's the part 2, this is E2. And we found our percent. Now, before I turn you loose to go start working on your progress checks, I wanted to just show you the highlights of the PowerPoint. So it goes on to the next topic, 1.2, massive spectroscopy of elements. Tells you what you really need to be able to do here. Gives you some example problems. You try out the example problem, you check your answer. The answers are here. Going over a few more things for 1.2, average atomic mass. How do you calculate it? Here's an example problem. Here, how do you calculate relative abundances? Here's an example problem. And then it goes on to 1.3, talks about what you need to know here. Basically, these are the empirical molecular formula combustion analysis problems. Gives you an example of how to, what you would need to do. Here is one example, gives you the solutions. You can check your answers as you're working on it as you go. 1.4, those composition of mixture ones, although we did partially in that first example of the free response problem. You can go through them. I also said, see that part of the examples in the PowerPoint. 1.5 is electron configuration and Coulombic attraction. So reviewing Coulombic force. Here's an example for electron configuration, you know, and gives you the answers and the solution and the methodology to it. So photoelectron spectroscopy here, same idea. Here's an example problem. What is the answer? Here's one that you have to explain. And this one I gave you the claim, evidence, reasoning format of how you should explain it. So you can check this out. 1.7 periodic trends, I gave you a few different examples. Here's one with ionization energy. And as you can see, these are definitely completely from old exams. These were prior free response questions. Here's the second part of it, doing the B part. Here's the third part, doing the C part. This example, though, from another free response test of a different year, showing you that it also incorporates the electron configurations in there. So as you can see, you have to do electron configuration for the iron 2 ion. And then this one talks about atomic radius. So different periodic trend here. And I also provided the scoring guideline solution so you can see what answers they would accept and how they decide which point you get. So here, these are directly from the scoring guidelines for you to check out. And you can Google and look at old prior free response questions to get yourself a feel of how they look. This one also incorporates Coulomb's law. You see in part C, Coulomb's law, justify using Coulomb's law. All right, you can specifically state it, or you can just talk about the magnitude of charge or the distance part of the equation. So that kind of goes through those particular examples. Here's another one talking about ground state versus ion configurations. And it talks about those isoelectronic series. So this is getting into that aspect of the periodic trends. And it goes through the solutions here. You can definitely check that out. This is a good study tool. Valence electrons, ionic compounds. What do you need to know here? An example problem, how you would work it out, go through the solution. And remember, the location and valence electrons are very important, of course, governing the typical charges that they're going to form. I also threw in here a slide about the solutions. Mainly what you need to be able to do is the molarity equation. You don't really need to be able to distinguish and do dilution just yet, but if you're starting out with a solution that has the molarity and you need to calculate grams from that or something, you should be able to use your molarity equation. And stoichiometry, we kind of went through that. You need to be able to do mole ratio. You need to be able to do chemical species amounts, grams, particles, or liters at, standard temperature, pressure in a balanced reaction. You need to be able to calculate theoretical and percent yields. You need to determine limiting reactants and amount left over of reactant, which would be the excess. So those are the highlights of what you would need to know for our quiz.